delay. Unfortunately, I had to set up the screen, and then we are ready to start. And I will try to recover some minutes, but I cannot recover all of them because unfortunately I have another lecture, or fortunately I have another lecture later. Okay, so the registration is started. Now let me share the screen. And okay, here we are, perfect. And then we can go on our webpage, my webpage, lecture notes, and the science of climate change. So the next lecture, we discussed a couple of weeks ago about the climate models, and we made a first example of a global scale model, and which it is a very simple one based on energy balance, as you may remember. And it was an exercise that we developed to demonstrate that actually these models are very complicated, but the complication comes from the fact that we want to model at the very local scale. And therefore, we have many cells, many elementary volumes with which we split the global volume of the Earth system into smaller pieces. This is the main complication that justifies the computational requirement, the very demanding computational requirements of climate models. But if we look at any single cell, and in the case of our exercise, it was only one cell covering the whole Earth system. If we look at any single cell, it's a mere application, just an application of conservation equations, which at the scale of the single cell are usually not so complicated. And their computational requirement, the individual computational requirement, is very small. In fact, we could show over the screen that we can easily estimate the average temperature of Earth at the global level with a very simple equation, very simple computation. And this concluded our treatment of climate models, which is very important because we need to understand how the science of climate change is translated into predictions, into models, and therefore predictions. The next lectures are dedicated to study with more detail the implications of climate change on single sectors like the water cycle and therefore the water sector, the energy sector. And then there is a lecture that is dedicated to a further look, a refined look at the history of Earth climate. And then there is a final lecture, if we will have time, which is dedicated to design of climate change adaptation actions. I said if we have time, because we have together, me and you, 3 more lectures today, and then there is next week, and then 27th of April. And then my part is concluded, so I'm not really sure if we can cover all of these. But in any case, the links will remain there for your interest and for your further assessment if you want to expand your knowledge about these topics. One important reminder, next Wednesday, my colleague Alessio Domenighetti starts the lectures. I think it is the day after tomorrow. So he will go for a couple of weeks in parallel, for 3 weeks in parallel with me. This is not a problem because we don't overlap. And what I am teaching is not necessary to support your understanding of what Professor Domenighetti will say. Just keep in mind that from this week, you also start lectures on Wednesday, okay? And you can find the overall timetable not here on my website, of course, but in the website of the University of Bologna dedicated to this subject. Now, about today, the next link would be climate change and water cycle. I skip this because I feel we don't have time to cover all the lectures, as I mentioned earlier, and then I will go to history of Earth climate. And the climate change and water cycle, it's a very descriptive lecture, and which describes what are the implications of global warming in particular on the water cycle in terms of evaporation, precipitation, sea level, drought, floods. It's once again very descriptive. There is no math. It's something that I leave to you to read if you are interested. And it was updated last time a couple of years ago. So it's a recent lecture, but not a very recent one, just to let you know. And you will see in the bottom of the lecture, there is the date of the last update. It was, let's see, and no, it is 21, so it's 5 years ago. Time passes quickly. But in any case, it's still very actual, but you have to keep in mind that it's, 5 years in the subject is already a little bit, okay? And as you see, there is no equations. There are no equations. There are a lot of figures and discussion of the implication in ocean circulation, etc. It is a lecture that required to me a lot of work, and it is widely read as you look at the counter in the bottom of the page, because first it's quite old. So it is 40,000 views. I think it's the most viewed page of my website, but it is already like maybe 8 years old, before the pandemics for sure. And also, it's a subject that is continuously evolving, so this justifies the interest of people. There is also to say that, water cycle is my field, and therefore it's probably, with respect to the other lectures that you can see on the links, it is probably one of the most informed in terms of recent scientific developments, and this probably justifies also the high number of readings. Okay, good. So, but we are skipping this, okay? And of course, at the exam, you will not find any question related to this lecture. It's skipped, but the links remain there. Now, next one, history of Earth's climate. Why this lecture? And first, at the start of this course, some years ago, before the pandemics, this was meant to be a cooperation between different teachers, a geologist, myself, a climatologist, and therefore the geologist proposed this lecture on the history of Earth's climate, which is indeed very relevant. I invited the geologist to deliver the lecture on this subject because it allows to get a look about natural variability. We already discussed that natural variability is a possible driver of climate change. And we call it natural variability, but we call it also natural change. So it is responsible, this phenomenon, for fluctuation or changes in the climate that are not related to humans. It's called natural, where the word natural is a bit misleading. It means without humans, without any attribution to human activities. And to give an example, can be given to volcanic eruptions, can be given to changes in solar activity, can be given to, as we will see, to changes in the inclination of the Earth's axis. So it can be due to the impact of meteorites. It is something that we call natural to mean, as I said, without humans. Why it is misleading? Because also humans are part of nature. So when we mention natural hazards, it's not clear what we mean with natural hazards, because a flood can be caused by humans, but still is natural. It's due to nature. It's a manipulation by humans of nature, maybe, but it remains a natural hazard. So when we say natural hazards, it's not clear if we mean that it's something independent of humans or something that is occurring in nature. And then even now, when we say natural variability, it's not very clear. And so I prefer to make it clear what I mean with natural variability. For sure, if we look at the climate change before 1850, at least according to our knowledge, cannot be attributed to humans, because we attribute human-induced climate change to CO2 emissions. And before 1850, before the Industrial Revolution, the human CO2 emissions were very limited, and basically not much changed with respect to the past. But in any case, with respect to today's human emissions, they were indeed a negligible fraction of it. And the real increase in human emission has been caused by the Industrial Revolution, and in particular when we started burning coal for producing water vapor to feed the water vapor engines. This was the big start. And therefore, in order to see what are the climate changes that are independent of humans, we need to look back at the far past. Unfortunately, as we already know, the instrumental period dates back only to 1850. So this means that we have observed values of climatic variables up to at most 300 years ago. And we conventionally assume that the instrumental period starts in 1850, as we already mentioned. Actually, there were records before than that. And I mentioned already to you the daily precipitation series in Padua starting in 1725. But we could also mention the measurements of the Nile River levels by the Egyptians 3,000 years ago. And they measured the annual max level of the Nile River for 600 years. And so we have some instrumental observations, but conventionally we say that the very systematic observation of climatic variables started in 1850. So this means that if we want to look back to the periods before 1850, we need to invent something. Okay, and we already mentioned three rings, paleoclimatic investigations, but we never went into the details of what these investigations, these reconstructions tell us. So I think that this lecture that is focusing on a deeper understanding of the climatic fluctuations of the past is very relevant, because if we want to really become expert about climate change, we also have to become aware of what are the jokes of nature intended without humans. And which means that even in a fully dehumanized system, Earth system, there is the possibility that the climate changes. And we need to understand how, because this makes us really very expert about climate change. We cannot become very expert about human-induced climate change if we are not as well experts in not human-induced climate change according to our knowledge. And therefore we click here. But if we click here, we go to Virtuale. Why? Because this lecture is not, we cannot make it open access, because there are some figures. I asked my colleagues and they said, no, please. Because, we are allowed to use and to distribute to students copyrighted material for educational purposes, but we cannot make it openly available for educational purposes, even for educational purposes, because if we make it open to everybody, it's more than education. It's also something related to dissemination, which is a different story. By the way, there are some figures that are in my website, and I will, not in my website, are here. I will show you the figure. I asked, it was published on Nature, I think, yes, on Nature. I asked the fee for making it publicly available, not publicly available, just to make it publicly available in a university lecture open to the whole world. And they asked me, I think, 260 euros of fee, and the university cannot pay for that. So I said, okay, sorry. I took your time for nothing, because, and also, I said no, because it's a concept that I don't like. I mean, Nature is one of the most prestigious journals, and it poses a barrier to education. It's not really nice. But anyway, this is the commercial world. So history of Earth climate, and then we get this this lecture, but I want to see it in presentation. Let's see. Presentation. Okay, this is good. I think this is perfect. So this is the name of my colleague, Veronica Rossi. She's professor here at Unibo. And the lecture is a bit distorted because it was prepared in 4:3, and here it's displayed in 16:9. And therefore you see that the logo of the university, the old one, by the way, is a bit stretched in the horizontal direction. Okay, it's not a big problem, just wanted to let you know. Okay, good. And now let's see. first of all, there is a premise in this lecture. Let's see if I can. Yeah. This is a table of contents. I'm not sure we can browse all of it. An important premise. I am not a super expert of this topic. And when I watched this lecture, I learned a lot of things which I didn't know. And therefore, just keep it in mind. I may be not very clear in some of these slides. I will tell you when I am not very prepared to discuss them. By the way, this is a very long presentation. I'm not sure we have time because I want to close it by today, possibly. And I'm not sure, maybe I skip some of the slides, but I wanted to make it clear that this is not my field, okay? So let's move forward. And this is an important premise, important for a geologist in particular, because the geologist had a lot of discussions about the methodology that we should follow if we want to understand the past. Because usually they look at traces, remains, in particular they look at stratigraphy in order to understand the past climate. But there is an assumption behind the use of these proxy data, tree rings, and the assumption is the so-called uniformitarianism, which means that the Earth, the evolution of the Earth system is a slow process. It's a slow evolution, which can then be recorded by looking at remains like lithological stratigraphy and rock stratigraphy, or sedimentary sedimentation, sediments of ocean, lakes. These traces, these indicators have evolved with a slow evolution. You understand that a stratum of rock, which means sedimentation and then maybe transformation, is a slow process. And therefore, we need to assume that this information was able to collect the changes that occurred during the evolution of Earth. But actually, there is also another theory which allows for the evolution to be also governed by shocking events. And these shocking events may be not recorded by sediments, because they are events that can evolve in a very short time. So, for instance, even the change in ocean level, it's something that we can monitor by looking at sediments if it was a slow evolution, a slow change. But if, for instance, the change in sea level was due to a sudden abrupt increase due to the rupture of some ice caps, for instance, sudden rupture, maybe that we cannot really see the evolution in these proxy data, in these indicators. And therefore, the contemporary view, this uniformitarianism was proposed already by Charles Lyell in 200 years ago. But indeed, the modern view is to admit that there could have been, or there could be, sudden changes in climate, which, if we look at the present, we cannot see in the past. So the present not necessarily is a key to the past. So this looks like a complicated reasoning, but I think you got the concept. So basically, we make these reconstructions, but there is uncertainty, of course, and we cannot exclude that some events, some changes were determined by events that are not monitored. Okay. For instance, we cannot know if there was a collision of a meteorite over the Earth some billions of years ago. some, let's say, millions of years ago. Because if there was, the crater probably has been eroded, and we cannot see the traces. So basically, we can see the sediments, we can see the stratigraphy, but these indicators cannot tell us whether there was a collision with a meteorite. And therefore, you understand, this is why we are still discussing whether or not the dinosaurs got extincted because it was the impact of a meteorite rather than a volcanic eruption, rather than something different. Okay, now let's look then, let's assume that we can get information by looking at geological records, so rocks, sediments, ice, glaciers, and these are an interesting option because it's a natural lab containing a lot of information which can lead us to understanding indeed the past climate and can also lead us to better understand what is the reliability of climate models, because we make a comparison between simulation by climate models and reconstructions of past climate. So it is indeed very helpful in order to make inference also to the extent of the human-induced climate change today. This is a photograph of the Scala dei Turchi at Agrigento, which has been widely studied, and it's also a very nice place. But there are several of these examples, even very close to here, and especially for sedimentary formations, there are several examples of stratigraphies that clearly indicate what has been the evolution of the rocks, and therefore also the evolution of the climate, because remember that it's climate driving erosion, driving sedimentation, driving everything. In particular, precipitation for erosion and sedimentation. But we will see that we can get information also on temperature, because precipitation can be in turn related to temperature. Okay, we already know about the great acceleration. So this change that we observed starting from 1850, you see that this graph for, this is again surface temperature, you see that these graphs start from 1850, and for the sea level, they start a bit later, and they usually start from 1900. These are direct measurements. And of course, we know that there has been an increase recently of temperature, sea level, etc., with a different gradient. You see, temperature, we already know these progresses. We know that the sea level started to increase already in 1850. But of course, the sea level increase is certainly related to temperature, but in a way that is sometimes not so linear. And therefore, it's also understandable that for some reason, we may observe different trends. But we already discussed this. This is an interesting representation, and it's a sketch that explains what is our current subdivision of the past into eon, epochs. Let me see. It's eon, eras, epochs, and periods. First of all, let's look at the picture on the left. It is what it's interesting now. And to us, first of all, the age of the Earth is about 4.6 billion years ago, okay? And so it's a much longer history with respect to the history of humans, much longer, I think 3 orders of magnitude, okay? And therefore, we tried to categorize the time since the formation of Earth to subdivide the time in categories. And these categories are identified through geologic records. This is the procedure that we followed so far. And first, we can divide the whole period in what are called eons, mega periods. And here you see the eons in the bottom, Proterozoic, Archean. These are called eons, and they cover a very large time span. You see that the Archean ended 2.5 billion years ago, and the Proterozoic ended about 400 million years ago. Then the subsequent eons are not mentioned here. And if you want to get informations about further information about what is displayed here, there is a Wikipedia page that is very comprehensive. What you see in the most recent period is the subdivision in Paleozoic, Mesozoic, and Cenozoic. These are eras. There is a further subdivision that is not displayed here in epochs, but what is displayed here is that each era is subdivided in periods. And the current period is the Holocene, which started 10,000 years ago. Okay, before the Holocene, we had the Pleistocene, which extended up to 1.8 millions of years ago, and then Pliocene, Miocene, Oligocene, Eocene, and Paleocene. These are the periods that form the era of the Cenozoic. So currently we are in the Cenozoic. If we are interested in the epoch, the current epoch is the Quaternary, which is a period characterized by glaciations. And the current period is the Holocene. Once again, these are determined, subdivided based on geologic records. You may have heard, and we discussed it already, that it's currently being discussed a proposal to introduce a new period called the Anthropocene, which would follow the Holocene. And it's a much debated topic, and of course there has not been agreement so far. First, because the Holocene started relatively recently, and the second, because the Anthropocene would identify a period that is characterized by a remarkable human influence on the geological history. And the main question is, what is the marker of it? So if we want to subdivide periods, era, epochs based on geological markers, what is the marker, the geological marker of the Anthropocene? If we look at sediments, if we look, what is the marker? And therefore, it is debated, but for sure, it is interesting to highlight that today we have a human influence that is much higher than we had in the past. And this is due to the fact also, as we will see, that the Holocene is very livable. It has been identified because the fact that the climate is very stable during the Holocene has favored the proliferation of a multitude of forms of life that left a considerable marker. Also remember that the Holocene started at the beginning of the warm period after the last glaciation. The last glaciation is not really concluded. We are in the tail of the last glaciation. But as I said, about 10,000 years, as I said in previous lectures, about 10,000 years ago, the temperature started to increase and the sea level rise to increase. In fact, if we look at the sea level rise 10,000 years ago, it was like 120 meters lower than today, sea level, not sea level rise, sea level. So the Holocene is a very stable period, which has favored also the proliferation of the human civilization. And this is why the human civilization grew up so intensively during these past 10,000 years. Humans have been lived over the earth for much longer. but during the past 10,000 years, I wouldn't, the civilization increased. Okay, and now I have an amnesty. Let me just check what is forgive me. Okay, it's easier for me to look at here. What is the age of the human species? I would say that it's okay. It's 300,000 years. So it's correct what I stated before. Humans have been living over the Earth for much longer. Okay, so this is in a way interesting, and keep in mind the age of the Earth and the age of the human species. These are important dates to be remembered. Okay, now this is the start of this lecture. It's an important recent development. This is the longer reconstruction of the temperature of Earth during the past 500 millions of years. Remember that when we say that the CO2 concentration has never been higher than today in the atmosphere, when we say that the temperature, the global temperature of Earth has not been higher than today, we refer to the past 500,000 years. So this goes back 500 millions of years. So our previous reference, meaning 500,000 of years, is in the far right of the figure, because you see that 1 million is like 1 millimeter in the figure. Okay, it's like 1/50 of the distance between today and 50 millions, which means that you have to split this interval in 100 pieces, this interval here in 100 pieces, and you get the temperature in the recent period, 500,000. Still, you can see here the increase after the last glaciation. You can see here the glaciation, temperature going down, and then the increase which occurred during the last 10,000 years. And indeed, if you look at the temperature of today, you see that it's higher, it's never been higher during this piece here, which is about 500,000. But the first thing that you see here is that we are in a cold period. And remember, in yellow, it's they mark the period without ice caps. The Earth has been without ice caps for much of its history, or let's say much of these 500 millions of years. And then you see that there are up and downs. And you don't see here a focus on the past 10,000 years. It's like 0.5 millimeter here, but we will make a focus also in other slides. We will make a zoom in this final part. But what we can really get here is first the value of this information that was presented about, I think it is, let me see, there is a reference here, probably not, Scott and Huber, it's 19, okay? It was presented like 6 years ago in 2019. And this is a figure that I asked Nature to make public, and they said they wanted 250 euros. So, and this actually is presented, this figure in the Smithsonian Museum, which is in Washington. And I also went on the website of the museum, but it's not public. It is described there on the website of the museum, but it is copyrighted, the figure. So this is really very relevant information. We will see how it was derived. Remember that previous reconstructions went back at least, at most, we will see some of the previous reconstruction, but they went back only a small fraction of this period. And so we see these up and downs, and we see that some points are marked. Let's see what are the markers. And okay, let me see. Okay, and here there are no, okay, greenhouse, ice house. Here the only difference is the the greenhouse periods are the periods without ice caps. Water without polar caps and water with polar caps. So we say ice house period, we mark with the name ice house periods, the timing with ice caps, and greenhouse period, the remaining parts. So you see that we are into an ice house period, and indeed we are within in the tail of a glaciation. So this is important to be kept in mind, because it means that indeed in the past history of Earth, but without humans anyway, we had quite different climate. But of course, the problem is to understand why. Okay, what are the causes? I talked about the marker 1, 2, 3, 4, 5, and you see here, and there is a first marker put at the age of diversification of marine life, Cambrian explosion, during a very high temperature period, because indeed the marine life was favored and is still favored by a warm water. We can understand if the water is very cold, of course, there is less possibility for some species to survive. We know, in fact, that the increase of marine temperature is a problem for water quality, because there is proliferation of several forms of life and organic species, which cause, of course, a degradation of the water quality. They marked with the number 2 the polar ice cap formation, and the first that we can document, and the second actually, but this one was very short. This one is a very long period with polar ice cap formations. So it would be interesting to understand what are the conditions, of course, temperature, but what determines temperature such that the polar ice cap can form up and persist for a long time. Actually, if you look, this is the longest time up to now with polar caps. So understanding what are the conditions leading to that, maybe a reduced solar activity, maybe there was a series of volcanic eruptions, because in the past we know that the volcanic activity was larger. And, we are talking here about 300 billions of years ago. So the volcanic activity was large. The volcanic activity is slowly declining because, of course, the activity in the nucleus of the Earth is becoming colder and colder, and therefore volcanic activity is slowly declining, very slow. And then with number 3, radiation of reptiles during a greenhouse period. Because if we move over the land, in particular, the species with a large size, they find it difficult to survive in a very warm period. So this is an hypothesis that we make, that the dinosaurs went under extinction, maybe because there was a very warm period. But again, it would be interesting to know what was the cause of that. Maybe the impact of a meteorite, we don't know. And then the number 4 is radiation of mammals, again, during a greenhouse period. Another greenhouse period, number 4, with a very high temperature. And you see the difference. I mean, we're talking about 20 degrees more of global temperature, because the current one is around 14.5. You see the tail of the figure. But if you look at number 3, it was 32, which means 18 degrees more. It's a lot. It's really a lot, because global warming is still a very important concern, but we are talking about 1.5, 1.4, 1.5, as you remember. So I mean, 18 more is something that is very relevant. And also, number 4, we know that there was a radiation of mammals, of large mammals, oversized mammals due to this. And then there is 5, it's the great acceleration. But actually, the great acceleration is the past 50 years. Here with the number 5, it's a bit misleading because number 5 is placed at the end of the minimum of the glaciation. But for sure, I mean, after number 5, in the last period, as I said, we got very favorable conditions for the life, which is one of the reasons of our prosperity today. So how did we reconstruct this? And first of all, as you see here, it was reconstructed by putting together several paleoclimate archives by means of several proxies. Proxies, what is a proxy data? We already discussed this. A proxy is an indicator of temperature. And it's not a measurement of temperature, of course, it's not an observation, but for instance, the width of a tree ring is a proxy. Of course, with tree rings, we don't go so far in the past, but a sediment core, so a sediment in the oceans, provide proxy data. And what kind of information can we use to reconstruct temperature? We are discussing now. And you know, what's important to get from this slide is that indeed several of these archives were analyzed and put together with a critical assessment. And therefore, through comparison of different sources of information, we hope that we gained a mitigation of uncertainty. There are a lot of research funds that are currently employed to get these proxy data, ice cores, ocean cores. A lot of money is invested because this is indeed something that is very relevant in order to understand the evolution of the Earth system and to make predictions. And it's a lot of research which we will discuss in the next slides. Okay, and so what kind of information can we use? Okay, first, deep sea deposits. Okay, so basically these archives, these paleoclimate archives, consist of geologic or biologic records. Geologic are rocks, sediments, biologic are corals, tree rings. It's material that preserve evidence of past changes in climate. And this is another example of stratigraphic analysis, and it refers again to Sicily. But as I said, there are many examples. And another very interesting information is delivered by the ocean cores. So we drill the bottom of the ocean in depth, in much depth, and we get these cores that are taken by ships that are drilling. And you see here on the right a figure of this core. So, but the core, of course, by itself doesn't say anything. We have to look for something that is trapped into the core. This is part, these campaigns are part of a global effort, which is presented at this website and iodp.org. Let me, sorry, iodp.org. It's very interesting. Okay, IODP, International Ocean Discovery Program, exploring the Earth under the sea, and there are a lot of figures, and there is a lot of information, and you see here expeditions. Let's see, expeditions, current expeditions, and there is here there is a description of the expeditions that are ongoing, apply to sail, because for researcher, but I think also to students, it's possible to apply for a sail, for participating at a campaign. I was invited once, but the problem is that you need 1 month time to dedicate to this, because these are long cruises. It's not just a couple of days. And therefore, I couldn't say yes. But indeed, this is possible. And there is also resources, etc. So it's quite interesting. I will show you the map. And let me see if there is in the history. No, there is a map somewhere of the cores that are now available. I will show you later because it's in other slides. Another slide. Okay, so again, here is the map. Okay, and also there is this YouTube video is another interesting thing. We lost the time at the beginning of the lecture, and so I cannot show the first minute to you, first couple of minutes, but you may be interested in getting a look. If you are interested in these topics, this could be also material for a final year project, like a thesis. If you, of course, the information is not so easy to be accessed, but it is possible if you're interested, depending, of course, on your background. You see that we have a lot of courses today available, and this is, remember, up to, I think these slides were prepared in 2019 or 2020. So it is continuously evolving. As I said, a lot of funding is dedicated to that, and it's a lot of money. You understand that it's really something that is demanding. And it's still delivering new information because, the ocean is very large, as you know, and therefore, when you try to, there are zones of the oceans that have been largely explored, but there are also other zones where it's a bit more complicated. And of course, under the ice caps, you cannot make this kind of investigation. There are other investigations that are carried out. So ocean cores are a first important source of information. And you see here what is a picture of the cores showing basically the stratigraphy. And there is on the right an example of 3 rings, which of course are not taken from the bottom of the ocean. But indeed, now it's interesting to try to understand how this information can be retrieved. So from this image, from the 3 rings, how can we get an understanding of temperature? How can we reconstruct temperature? This is indeed something that is interesting, but let's answer this question a bit later. Now, this is another example. It's the ice cores. And there is an intensive research activity in Greenland and Antarctica dedicated to drilling ice cores. In the same way as the bottom of the ocean delivers information, also the ice cores deliver a lot of information for the composition of the core. And I will give you more details what I mean by composition. And also for the particles that are trapped into the ice. For instance, dust is trapped into the ice, and analyzing dust, we get information of the past climate. And here there is again a link to a blog post, which is very interesting to read, very easy. It's very descriptive. And you see here each season's snowfall has slightly different properties than the last. These differences create annual layers in the ice, and this is what we inspect. And of course, still open the question how to inspect them. Okay, and this is a whole picture of the whole paleoclimatic archives that are available in this website of the National Ocean and Atmospheric Administration of the United States. One interesting thing of the governmental agencies of the United States is that the material published by them is all open access because they are required by law. So when you get information and pictures from the United States Geological Survey, from the federal administrations in general, unless it is differently specified, because they may have used copyrighted information, but in this case they explain, make it clear. Unless it is differently specified, everything is public. So when I see figures, for instance, if you look at my website, it's rich of figures that come from the National Ocean and Atmospheric Administration, NOAA, or other federal agencies. And this paleoclimatic archive is very easy to be used to retrieve data. And they have different symbols depending on the type of archive. So 3 rings are indicated, I think it's indicated in green. Not sure really, we should check. But it's either green or blue. I think the blue indicates probably the sediments, and then the sediments or stratigraphy. And then there are the ocean drilling campaigns, which I think are those in red, while those in blue should be, it's dark blue, the ice cores, etc. Anyway, you see that the website can be explored. Let's see if it is easy to be shown. NOAA Paleoclimate. Yes, it is this one. Paleoclimatology, and there is, I think I already presented to you this website. This is the map of the paleoclimatology data, and it is still loading. I think you see here the different proxies, and now it's not it's not displaying the data, but visit Paleo search for additional data not shows on this map. I don't understand why it's not presenting the spots, but anyway, if you look at it, it is very easy to be got, and we could see for Bologna, for instance, Bologna, Italy, and then we can zoom out. And let's see if by zooming we get some, yeah, and here you see some information. And then if you go over here with, I think, location. Okay, anyway, this can be browsed and explored, but let's close it. Very good. Okay, so this is a summary slide, and so in order to present the information that we can extract. So from the marine sediments, we can get these proxies: chemical composition, stable isotopes. I will describe the stable isotopes very soon because they are very interesting. And then particle size, and fossil and fossil as pollen and spores, micro, meiofauna, malacofauna, etc. So, and then there is for ice cores, dust, gas concentration, again stable isotopes. Speleothems, stable isotopes. And then lacustream sediments, chemical composition, again, stable isotopes, particle size, fossil as pollen and spores, plant, macro rests. So these stable isotopes indeed seems to be something very interesting, very good. And now it's okay. This is a further specification of this slide, and let's here the stable isotopes are highlighted and the fossils are highlighted because we want to discuss now what is the information that we can get from them, and in particular from the stable isotope and fossils. And remember that usually the proxies can be divided in two categories, two large categories, direct and indirect. As usual, classification helps to remember and better understand the information that can be delivered by each observation. And we say that the proxies are direct when they consist of atmospheric gases trapped in the layers of the ice cap, and in any case, it's something that doesn't need to be calibrated. We call indirect the proxy data, the information for which calibration is required. What does it mean, calibration? Calibration means that the relationship between the indirect information, like, for instance, stable isotopes, which we will discuss in a moment, the relationship between this information, indirect, and temperature is something that needs to be expressed through a regression. Regression means that in some way you find a relationship relating the indicator, the proxy data, with the temperature, but this relationship is parametric. This means that it's like a straight line, for instance, which is a parametric relationship because a straight line is governed also by the intercept and the slope. And this intercept and the slope for the straight line are parameters. Parameters that when we want to fit data, we calibrate. Calibrate means that we found the optimal values of the parameter representing the data. So this is calibration. It means that I develop a model to relate the proxy information with temperature, but this model needs to be adjusted in some way. This is calibration. Why? We say direct when no calibration is required. Because if we want, for instance, get the CO2 concentration, the CO2 concentration can be taken in a direct way because some gas is trapped in the ice cores, and then we take these small bubbles and analyze the CO2 concentration. There is no calibration, it's just a measurement. While CO2 concentration can be related to stable isotopes, and I will show you what they are, but through a regression for which calibration is needed. What is the problem of calibration? The problem of calibration is that I need some information to tune the estimation, to calibrate the regression. I need some information. So some of these, for instance, some of these relationships are calibrated by using observed data after 1850. And therefore, the relationship between temperature and stable isotopes, I calibrate it by getting recent observations, and then I extend this calibration to the past. And this is the problem of calibration. I need some information. And I also need to assume that the shape of the relationship remains unchanged during time. Okay, and you see this is direct. Atmospheric gases trapped in the layers of the ice caps, and indirect calibration is required. Very good. This is another example of ice cores, and once they are taken, they are conserved, of course, at the proper temperature, and their analysis may last for several years. And of course, depending on the position in the height of the core, you have reference, you refer to a different period. Very good. Now, this is an example and of an information about direct information about CO2 concentration that was taken by a Vostok the Vostok core, ice core, Carota di Ghiaccio is the name in Italian. And this core is a very important one because we could analyze the CO2 concentration in the air bubbles, as I mentioned earlier, directly. And therefore, we were able to conclude that in the past 500,000 years, CO2 concentration was never so high. So we got to a similar value than with respect to the one of 1950 in the far past. We see that in the past there have been up and downs, a lot of them. And of course, it's interesting to wonder what was the cause, but now we have a level that is much larger. And, we are not yet close to 2 CO2, but usually we indicate with the 2 CO2 a value that is twice the value of 1950, and therefore about 6 parts per million, 600 parts per million. But we are already at something that is about close to 1.5 CO2. And however, as I mentioned earlier, this goes back only 500,000 of years. And therefore, we know that indeed in this past 500,000 of years, we never got a so large global temperature. But of course, 500,000 is nothing with respect to the 500 millions of the previous picture. But this is, really an important core, and the depth of the core was 2.2 miles, 3 kilometers. It's something interesting to imagine that they were able already 25 years ago to get a carrot that is like 3 kilometers high. Yeah.
So this graph is directly derived from this expedition.
Yes. Yes.
This report.
Yes. Yes. And you can find more information here. So search Vostok. Vostok ice core. Okay, and unfortunately it's in Italian, but you can write the Vostok ice core extracted in Antarctica until a depth of 3.6 kilometers in 1998 provides a record, a climatic and atmospheric record that is very detailed, that goes back to more than 400,000 years ago. And it was an ice core that was, the mission was by Russia and France and the United States, and has permitted to analyze 4 glacial interglacial cycles. It was a very interesting exploration. And here there is a lot of information, as you see, and the location. And this is, they went almost to the bedrock under Antarctica. And you can find a lot of this information over the web, but there were several other missions after that. Okay, and you see here an interesting thing in this figure. I did not make it on purpose, but let me just open it because it is anticipating a slide that I wanted to show you. What is showing this picture? The isotopes of oxygen are more than 1, and they are stable. What does this mean? When you look at an atom, the number of in the nucleus of protons and electrons, but the number of protons in particular, is not fixed. There are atoms of oxygen that have 16 protons and atoms that have 18 protons. And these are stable. So the number of protons identifies an isotope. So we say O16 is the isotope of oxygen that counts 16 protons in the nucleus. And stable means that the number of protons for these two isotopes doesn't change. So an isotope O18 cannot lose 2 protons and become an isotope O16, while instead carbon-14 is subjected to decay, as you know. And by looking at the decay of the carbon-14, we can date some objects. But these isotopes instead are called stable, and it's not only the isotope of oxygen that is stable. There are other isotopes of other elements like deuterium. But what is interesting is that the isotope O18 is heavier in weight than the isotope O16. Okay, so what does this mean? It means that when there is evaporation, there is a preferential evaporation of O16. So in the ocean, let's look at the left figure. You see that the blue arrow, the light blue arrow, starts from O16. Why? O18 remains there because you need a much larger temperature. Of course, if the ocean gets depleted by O16, then also O18 evaporates. But you know, evaporation causes a decrease of temperature. And therefore, what happens in a normal situation is that O16 evaporates, and then temperature goes down, and there is no evaporation of O18. Or if there is evaporation, it's much lower than the evaporation of O16. So what happens is that O16 evaporates, and then it goes over the land. Over the land, it condenses, and it rains, and through the rain, O16 comes back to the ocean. This is in the left figure. But let's look at the right figure. What happens if there is a cold period is that the rainfall doesn't go back to the ocean. It remains trapped in the ice cap. And in fact, in the ice cap, we find a lot of O16. And therefore, if there is O16 trapped in the ice cap, there is an enrichment of O18 into the ocean. And therefore, if we find in the bottom of the ocean sediments with more O18, it means that it was a cold period. Do you follow that? It's very interesting. I was fascinated when I learned this from my colleague. And indeed, I could understand. I have been listening to people talking for more than 20 years about stable isotopes, but I couldn't really understand what was the mechanism behind it. And in this way, I can easily understand. So if you find in the ocean a good combination of, it's not, the ocean is not rich of O18. There is a good combination of O16 and O18. This means that the climate was warm. If in the ocean you find a lot of O18, it means that the climate was colder. And there is one thing that this figure doesn't show, which is the fact that if you get some evaporation of O18, which it can happen, it is heavier, of course, in the clouds. And therefore, as the clouds travel over the land, it is the first that rains down O18, and therefore typically doesn't reach the polar caps. And if some O18 evaporates, then it rains down and then goes back to the ocean. So basically, O18 is not trapped into the ice caps. This is something interesting, and I got it just by chance here. And I think this figure is clearer than the figure that I will show you later on. So it was a good thing that we found it. And then here it's explained. And also it is explained, okay, I use the term protons to indicate both protons and neutrons. Sorry for that. Okay, it was a little bit imprecise. The electrons are those that turn around the nucleus. The nucleus is formed by protons and neutrons, and O18 and O16 have a different composition in terms of proton and neutrons. And also another important is the deuterium and hydrogen. Also, there are stable isotopes in hydrogen and deuterium. And then here it's explained how they estimate the past climate, but I think that here my slide is clearer than that. So let's look at my slides now, okay? And then I move forward to jump to the relevant slide, and then we make the break. Here is the relevant slide. Let me just see. Okay, I think, sorry, 1 second. Okay, let's keep this for now, but I think we already discussed this. That's fine. So indeed, the next slide is what I am interested in. So basically, look at the second with the blue rectangle at the relationship. We start from a ratio between O18 and O16. O18 is lower in terms of numbers, in terms of composition of water. And therefore, we start from the relationship in the standard mean ocean water, SMOW, okay? We take it as a reference in the blue rectangle, right-hand side. You see that there is, at the denominator, there is this ratio in standard mean ocean water. At the numerator, what you find is the difference between the same ratio in our sample. So we take a sediment, and then we compute in the sediment the relationship between O18 and O16. So this is the ratio for the sample, and we make the difference with respect to the standard value. So this difference at the numerator is divided by the standard value. This means that if the result is positive, it means that in the sample there is more O18. So it was a cold period, because more O18 in the ocean. It was a cold period. If the difference, and therefore the result in the square brackets, is negative, it means that it was a warm period. And then it's multiplied by 1000, and we call the result delta O18, so difference in O18. Again, delta O18 positive means cold period, negative means a warm period. And the same delta can be computed for deuterium. It's another stable isotope, or for the stable isotope of hydrogen. Okay. Very interesting. Okay, and here again, the same relationship. Okay, let's see if I was correct. When delta is positive, the sample is enriched in heavier isotope. I think I was correct, but it doesn't say what I said, that the climate is colder, but it is, okay? Because when it is collected, the sample in the ocean, this is the result. When delta is negative, the sample is enriched in lighter isotopes, and therefore climate is warmer. And therefore, delta value fluctuation through time from layer to layer. So we go deep into the layers and we see the fluctuations in the stable isotopes. And the good thing is that they don't decay, they remain there. And track changes in climate, mainly temperature. Okay, but these stable isotopes are not only in the sediments, can also be included, as we discussed earlier, some slides ago, into the corals, etc. So this is the rationale behind the isotope analysis, and the paleoclimatologists measure difference, delta, in oxygen isotope concentration to reveal past climate. And here you see some examples. And this goes back, this example, to 800,000 years ago. And you see here current temperature. I'm not sure it is. No, it's not. It's not reported here because this graph goes back from 0 on the right, the graph in green, the green one, and okay, it's temperature and temperature change. These are the same graph, but starts from the right to from 1950. So basically, we don't have here the recent increase. I would say that the recent increase is larger than the temperature that we see here. And this goes back again 800,000. Again, it's temperature change. And here there is a mention to different methods for estimating temperature. I don't know them. Actually, there is the reference to the paper, but I don't know. You know, when you reconstruct, you see that you have two lines in the graph on the right, because when you reconstruct, this is calibrated. So basically, depending on the type of calibration that you use, you get slightly different results. And it's calibrated because we mentioned earlier that the difference in isotope concentration is not directly related to temperature. We have to find a regression equation. Okay, interesting enough. Now, there is also the opportunity to measure these differences in isotope concentration, not only in the ice cores, but also in the foraminifera. Foraminifera are coral fossils. So by investigating, we find these fossils in the bottom of the oceans. By investigating the composition, isotope composition in foraminifera, we get similar information. And this similar information, but complementary, have been put together in order to reconstruct the curve with which we started this lecture that goes back 500 millions of years. And it's interesting because these shelves put together to form CaCO3, put together ions from calcium and CO3, which are dissolved in seawater. So when foraminifera calcifies, many environmental information is stored in the chemistry and also isotopes of oxygen that compares as an element of CaCO3. Okay, let's make the break now up to 3 o'clock. Okay, now the slides that follow present several results that we obtained by analyzing the information from proxy data. And in particular, we will discuss some zoom over certain periods of the past, because it's interesting to focus on selected periods to understand some particular situations that we could reconstruct that basically depict conditions that are very similar to what we are experiencing today. So conditions where there was some warming, there was some particularly cold periods. So let's see. This is again a detail of the behaviors and the features that of the informations that can be derived from the deep sea chord successions. The interesting thing is high sampling frequency. High sampling frequency means that we can get a good detail over the timing of the changes. So we can get information that refers to very short periods, typically the year, because it's the snow season that brings a particular information related to that season. So in each individual snow season delivers the information. So here we can see a typical reconstruction that goes back to 400,000 years, derived from ice cores. This is from isotope concentration, marine cores, sorry. And this is something that we already anticipated. In this particular case, we see two reconstructions, and by two different cores, which show some differences in the reconstruction, but actually the scale is different. So let me just check. It's one is depicting a temperature scale ranging from about 10 to about 17, while Epica is colder, because indeed these are marine cores, so reflect different locations in the ocean. And therefore, what is interesting to see is that, of course, there are differences depending on the location where you sample the sediments. But what is interesting is that the oscillations seems to be coherent. So it means that these two cores, while providing different scales of temperature measurement, provide coherent pictures of the changes of temperature in the past a long time, which are related to something that we need to understand. Here there is some more details related to the composition of isotopes into the shells. And in particular, here it refers to the isotope composition of the shells of fossils. And what is highlighted here is that the effect of temperature means that with cold climate, we have an increase of O18 into the shells, because there is an enrichment of O18 in the ocean. And which means colder climate. And in the ice volume, if we have more ice, we have indeed, again, an increase of O18 in seawater and the shells. And basically, here there is a volumetric effect due to the fact that the O16 is trapped into the ice caps, and there is an effect due to temperature because temperature has also an effect on the biological feature of the shells. But anyway, when we look at the composition of the isotopic composition of the shells, we can get information on the composition of the seawater and therefore the temperature. This is not adding much information with respect to what we discussed before. It's just to highlight that the isotopic composition can be extracted by water trapped into the sediments, or in this case, it's biological remains that trap anyway isotopes from the surrounding environment. So basically, the take-home message is that the records, the isotopic records, in particular of the delta O18 from the shells of foraminifera, provide a quantitative measure of the combined effect of changes in ice volume and the temperature of ocean water, which means that ocean basins where sediment deposition is uninterrupted provide continuous record of climate history. So if the delta O18 is positive, Earth was colder than today. This confirms what I anticipated before. And if it is negative, Earth was warmer than today. And the reason is what we already discussed. Everything is clear, apart from maybe, yeah. Yes.
Is foraminifera regarded as a direct or indirect?
Everything is related to isotopic composition is indirect, because you need a relationship relating temperature to the isotopic composition of seawater. And usually it is calibrated, this relationship, by referring to today's measurements. So basically what we do is from 1850, from when temperature measurements are available, we relate temperature measurements with isotopic composition in the ocean, which is measured because in the sediments we have also the isotopic composition from 1850 to today. So we have 200 years of measurements of isotopic composition and temperature. And then for the past, we have only isotopic composition, but we can estimate temperature by using the regression equation that we calibrate from 1850 to today. So basically, let me just, because I see that it's not very clear. So let me make a picture here. So basically, what we have is a time scale where you have 1850 here, 1850 here, and then you have today here, and then here you have the past. And now let's depict here the temperature, and here the delta of 18. Okay. So when we take an ice core, the ice core covers this period. Okay, this is the period covered by the ice core. Ice or sea bottom core. Okay. Let's write sea bottom because we were talking about foraminifera. Sea core. Okay. And therefore you can make here, for simplicity, let's take a very clear relationship, an increasing one. Okay, this is delta O18. Okay, and then from 1850, you have also measurements of the temperature. Okay. Measured T. Very good. Now you can calibrate a relationship, and this relationship is t long time is a function of delta O18. Delta O18. Okay. So basically you can calibrate this relationship. Okay. So for instance, this relationship may be a straight line. Okay. And therefore you can show this relationship here. So let's suppose that we calibrate this straight line, which reproduces the measured temperature depending on the isotopic concentration. And then we can go back to the past here. As this is reconstructed. Reconstructed. And direct. And this is calibrated. So, for instance, the relationship may be temperature long time is equal to an intercept A plus B delta O18. And then these two are parameters which are calibrated. Parameters calibrated. This is just an example. So basically, I have a couple of observations, isotope, temperature, and I calibrate these parameters. And in this case, the regression line is linear, it's a straight line. And then you can go back into the past.
Is increasing as temperature is also
Yeah, okay, this is not okay. This is not good. This is not a good example. Yes, correct. And so this is just a depiction that I wanted to make to give the concept. But yes, you're right. Delta O18 is increasing for temperature decreasing. So I should have changed, but I don't want to make it very complicated. But the correct one would be something like this. Okay. You are still in doubt? So, thank you. You know, calibration is something that it is usual in Earth system modeling to build models, and these models are almost always parametric. Parametric means that you have to tune them, to calibrate them. This is typical, as I said, in Earth system modeling. We use parametric models to predict floods, to predict earthquakes. Prediction of earthquakes, you know that it's a bit tricky, but to predict contamination of soil, water, we use parametric models. And then calibration means that you get an estimate that is unbound. It's not a measurement, it's something it's reconstructed. Okay, good. But yes, your comment about the opposite sign of the slope is perfect, is very appropriate. This is a figure that explains the isotopic composition. And this is a bit more complicated with respect to the one that we saw before, but it's saying the same thing. So in an interglacial period, we have ratio between the isotopes. It's not very clear. Is O18 divided by O16, what you read here, that is unchanged. There is preferential evaporation. And here you have preferential precipitation with some O18, which falls down before then the lighter precipitation that is reached of O16, which goes more into the land. Precipitation with less O18, and then in an interglacial period you have the return of O16 and O18, so the ratio is unchanged. In a glacial period you have O16 reached ice, and therefore it is trapped here, and then you have the water that is enriched in O18. Okay, and then you get values with high O18 within foraminifera shells, but not only in foraminifera, also in the other proxy data that we use. Okay, again, this is something that we already have seen before, and it's now we understand what is stable isotopes analysis. But there is not only stable isotopes, there is also fossils like pollen, spores, and the information that they deliver is different from the information that is delivered by stable isotopes, which is a good thing because, as I said, we need to put together different sources of information. Okay, and then let's talk about fossil records. And fossil records, which again present several sources of information. And this is interesting because we can compare the present day distribution with the distribution of fossils into the past. Why this is interesting? It's interesting because the fossils, of course, the shells grow up in different climatic conditions. So there are temperature, climatic conditions, in particular temperature, which are favorable to the growth and evolution of certain fossils, and climatic conditions under which they die. So if we see that, for instance, the Arctica islandica, which is a particular shell that we find in the late Pleistocene in Liguria, and now it's no more there, it means that in the late Pleistocene there were favorable conditions for the Arctica islandica to grow up in that region, and now there are not favorable conditions. So another example is this fossil, the Persistrombus hiatus, late Pleistocene in Italy, and it was about 130 kilo years before present, which means now it's no more there, which means that these fossils, so the Persistrombus, which now we find in Africa, in the zone that is marked in yellow there, in the past, in that period, they were in Italy, which means that the yellow arrow, which means that the climatic conditions in Italy 130 kilo years ago were similar to the climatic conditions near the equator today in Africa, which means warmer temperature. Same thing, the Arctica islandica grows up in cold climate. And in fact, today's distribution is around Iceland, around Sweden, in the North Sea, around UK and Ireland, but about 30 to 18,000 of years ago, it was in Liguria, which means that Liguria in that period had a colder climate than today. And this is not a reconstruction that is based on isotopes, as you see. It's just based on the distribution, a comparison of the current distribution of fossils with respect to the previous distribution, which we can find in the analysis of geological stratigraphies. And this is, again, indirect. It's not a direct measurement. Basically, what we say is, this tells me, this distribution analysis tells me that the temperature, the average temperature of the sea around Iceland today is comparable. I assume it's the same temperature that I could see in Liguria 30,000 years ago. And it's a parametric relationship because you basically say A equal B. It's a anyway an assumption. It's something that in a way, I try to calibrate. And this is something that integrates the information delivered by the isotopes. So it can confirm it, it can correct it. So it's important to put together several sources of information. And also, vegetation and pollens and other information. A record of past vegetation covers can be preserved within deposits thanks to the analysis of macro remains like seeds and pollen grains. And again, if we see that a particular species that today is confined to a certain climate was present in a certain time in Italy, it means that the climate in Italy at that certain time was similar to the climate where we can find today these species. And so we can find these traces through seeds and pollen grains. And then there is also, the analysis of the vegetation. And the vegetation is compared at our latitudes with the vegetation at high latitudes, for instance, and we can see remains of that vegetation from the analysis of stratigraphy, from the analysis of seeds, etc. And then we can compare also this vegetation type. Okay, so basically this is what is shown here is a comparison between the Mediterranean forest and the tundra. And of course, by looking at the remains, we can reconstruct temperature, which is also interesting. So this is basically interglacial and glaciers vegetation landscape. This is another focus which allows me to introduce an interesting reflection on the characteristic of our climate during the Holocene. So I anticipated earlier, first of all, let's look at the scale. We go back with this reconstruction to 60 millions of years ago. And you see in this figure, it's indicated also the cores, the information, the origin of the information. So there is Epica Dome C is a core, and then there are other contributions that are mentioned here, which refer to other cores. It is indicated here the period covered by the existence of the Homo sapiens and the existence of the Homo genus, which is longer. The time period covered by the Homo genus is superimposed to that of the Homo sapiens and goes back much further in the past. What is interesting to see today is, first of all, there is the historical period depicted here. And with this zoom, we can see what is indeed the increase of temperature related to the Great Acceleration. But the striking information that we see here is the stability of the climate, stability of temperature during the Holocene. This is confirmed. You see that it is much more stable, the temperature in the past 10,000 years with respect to the whole development up to 60 millions of years ago. Actually, there are other periods, if you look at the whole graph, where the temperature was not much changing, like this one, but here it's longer. There is another thing that we have to keep in mind here. The historical period is, of course, characterized by less uncertainty. But also, if we go back to, because this is a logarithmic scale, and therefore the extension of the that you see here is not comparable to the same extension that you see here. This covers some millions of years. But actually, if you look anyway into the past, you can see that indeed this period is characterized by a stable temperature, because you see that there is a lot of more variability, but unfortunately, here uncertainty is very reduced. Here is larger, but still very reduced, because uncertainty increases as you go much further into the past. And therefore, I mean, the conclusion that we try to reach is that we cannot say if this is unprecedented. It looks like if you go back up to here, up to the existence of the Homo sapiens, which is more or less here, up there, indeed it looks like this is a very favorable period, because it's stable and also the temperature is higher. Of course, during glaciations, it was not so favorable. But what it is indeed important from this figure is to get this message. The Holocene is a period that is characterized by a relatively stable climate. And even if we look at the recent past, there is an increase, but this increase is not really a new thing if you look at the Holocene. Because as you will see, also during the Holocene, there have been some fluctuations. So what is the message? The message is this natural variability seems to be able to induce perturbations in the climate that are comparable to the perturbation that we are experiencing today. So it could be that, this gives room to the interpretation that the human influence is not as significant. On the other hand, we have to keep into account that we cannot exclude, according to our knowledge, the fact that the human influence is significant. And therefore, in view of the uncertainties and in view of what we are observing now, this consideration shouldn't lead us to say, well, the human influence is negligible. Absolutely not. What is important, aware to keep as a take-home message, is that potential natural variability can cause similar fluctuations, but at the same time, we have to intensify our effort to limit the risk that the human variability, the human-induced variability is the reason of what we are experiencing today. So it's a reasoning that is a bit complicated, but it's important on the one hand to deliver the message that as scientists, we have to recognize that natural variability may be important. We have to recognize that natural phenomena can cause perturbations that are much larger than the perturbations that we are looking at today. But this doesn't allow us to conclude that the current perturbation is due to natural variability. This is not a consequential implication. It would be wrong to say that given that in the past we didn't have ice caps, well, maybe that we are going to have no ice caps in the future for natural reasons. This is not a legitimate conclusion. One thing is to say we cannot exclude that natural variability potentially may be responsible. This is one thing, but on the conclusion that natural variability is responsible of the climate change today would be wrong. Okay, so this is why people are still doing research on this. This is why we are still using vessels to get ice cores, to get cores from the bottom of the ocean, because we need to understand better. And meanwhile, we have to make any effort to mitigate the risk that humans are perturbing the climate. This seems to be like a logic conclusion, but on the other hand, this conclusion is the subject of an ongoing debate, which is very, it's not an easy debate. It's very controversial. And you see the recent development in the politics of the United States, how much controversial they are, and they are also centered on this interpretation. What Trump says is that humans are not responsible. So why should we reduce the burning of fossil fuels? Actually, there are several reasons why we should reduce the burning of fossil fuels, including the fact that we have to become energy independent, include so political reasons. including the fact that burning fossil fuels causes also air pollution that is very significant. Okay, so take-home message, there are several applications of these slides, and because my colleague went on in the discussion of the stability of the climate in the Holocene with a lot of details, you see here there is a focus on the interglacial periods, and then you see here there is a focus on the stability of the climate, and then the slides shows what we already know. During the last glacial maximum, it's an interesting picture, the shoreline of the Mediterranean area. The sea level was minus 120 meters below the present level. Okay, I am skipping this one because it's a detail on an impressive number of records that have been collected from the ocean bottom related to sediments, and which can lead us to measure the global ice volume and deep ocean temperature during the last 5 million of years. It's another zoom. Okay, and I am not giving the details. This is one of the results, and which shows that there is this is the time scale is kilo years. So it's starting from it's a zoom on kilo years before present, and it's interesting to see the progressive, stronger glacial sign through time, and that there is an evidence of climate cycles superimposed into a general cooling trend. And this is interesting because it shows this kind of superimposition, so several fluctuations that are superimposed. And it is interesting because the human influence is another reason for climate change, for sure. I mean, for sure it is. And it's important to try to avoid that the effect of human influence is superimposed in a negative manner to natural variability. This is what also climate scientists keep saying, like, be careful, because it may be that indeed natural variability is significant and human influence is exacerbating the impact of climate variability that is already quite significant. This is another of the zoom that I mentioned to you, and let's skip this. And now, an interesting concluding reflection. Is it so stable, the Holocene, then? Okay, let's look at some details. And here it's a zoom on the Holocene, and obtained with high resolution stable isotope records. And so what we see is that indeed, if we zoom on the details, there are some cycles indeed in the Holocene. If we go back to the previous slide, we don't see them. But with this zoom, we see that there are up and downs. And here you see the reconstruction from several different ice cores. But what we see indeed is some oscillations, minor oscillations, minor if compared to the oscillations that we experienced during the last glaciation, but still important oscillations. And the most important about 8,000 years ago, okay? And you can see them over the figure. Let's see with more details. These are climate anomalies during this event that occurred about 8,000 years ago, with the warmer Southern Ocean and the colder Northern Ocean. And also you see in the bottom figure the changes in terms of drier and wetter. So it was, the distribution is a bit puzzling because it looks like there was a band around the equator and from the equator and the latitude of the south of Italy, where the climate was drier, and a distribution of sites where the climate was better. And it's interesting because we need to gain an expectation of what may happen. So the Holocene is stable, okay, but there have been some minor fluctuations. What happened during these fluctuations allows us to anticipate what may happen in the future if global warming keeps going. And it's not so easy to understand what may happen. I mentioned to you already that the influence of global warming on precipitation is not so clear, depending on the type of precipitation, long-term precipitation, annual precipitation, rather than seasonal precipitation. And then this is what I wanted to discuss with you today. This is showing the occurrence of warm periods in the recent past couple of thousand years, recent past. In particular, here it's shown the Roman warm period and the medieval warm period. These are very well-known warm periods. To give you an order of magnitude, during the medieval warm period, the temperature is believed, at least in Europe, to have been higher than today, the mean temperature, mean annual temperature. Why we say that? Because we had some records taken by monks which describe the distribution of the vegetation. And we know that pines in the Alps were growing up at a higher altitude than today. We also know that, for instance, the name of the Mount Cervino or Matterhorn derives from Mount Silvanus. Silvanus means forested mountain. We know that people were walking from the Broye, Cervinia, to Zermatt without touching any ice, because we have reports that people walked through the Colle of Teodulo without any need of wearing winter shoes. And they report that they could walk without seeing any snow. Today, even after the retreat of glaciers, this is not possible. We need to cross a glacier in order to travel from Cervinia to Zermatt. And there are other of these witnesses that prove that probably during the medieval war period, the temperature was a little bit higher, not very much higher. I mean, we are not talking about 10 degrees, but if today we are at 1 plus 0.4, we guess that it could have been some fraction of degrees higher, like plus 1.6, 1.7. This justifies a significant retreat of glaciers. About the Romans, you know the information or the say that Hannibals could bring elephants through the Alps. We don't know if it is true, but it is possible if they had no glaciers at that time. But we know for sure that the Romans, for sure, we in a way postulate that the fall of the Roman Empire could have been caused by worsening of the climate. Remember that statistically and also physically speaking, when there is a decrease of temperature, it means that there is an increase of floods, an increase of rains, heavy rains, and therefore it is credible that the Romans the society of the Roman was based on agriculture, and these societies are very sensitive to changes in climate. Also, our modern society is sensitive, but also at that time it was very sensitive. So it is credible that they collapsed for the onset of some very bad weather. For sure, we know that after the medieval world period, there were economic crises caused by the fact that after 1500, there was an increase of flood frequency, and previously, people have invested a lot of resources over agriculture because the weather was very warm. And therefore, it is credible that this worsening of the climate, which culminated with the Little Ice Age that you see depicted there, which is proved by several reports, several recent reports, because the Little Ice Age terminated around 1750. There are a lot of reports that explain that this Little Ice Age caused several economic crises. The Casata d'Este here in northern Italy indeed collapsed because of the damages that they got from repeated flooding of the Po River. So, and in the right, you see the picture of the Venice Lagoon that was completely frozen and people skating over it. And you know, this is something that we never experienced in the past 200 years. It looks like around 1800, they got indeed several times the opportunity to skate over the Venice Lagoon. So the medieval world period, there is a lot of information over the web. It's something that is interesting because it's another example of natural variability. And we don't know the causes again. And even if it is relatively recent, there is another thing that we don't know. We don't know if it is global, if it was global or not, because the reports are from Europe. From the Americas, we don't have any report about that time. The only thing that we know is that, but it's not related to this time, is that also the Maya civilization probably was collapsed. They collapsed because of very long droughts, so very dry weather. Okay, so now there are some slides dedicated to the discussion of what could be the cause of these changes. And I don't think we need to spend time on this because there is no agreed conclusion. And there are several hypotheses postulated here, changes in the Earth orbit, changes in plate tectonics. This is possible. I mean, the movement of the continents, it's possible that it causes climate changes, changes in sun strength. I mean, there are several hypotheses that are being analyzed. And there is also the Milankovitch theory. Milankovitch dedicated its life to studying the climate variability induced by the changes in the Earth's orbit, and in particular changes in eccentricity of the Earth's axis, obliquity, and precession. And here it is explained why these changes, even minor ones, could be very important. And these changes may be induced by changes in plate tectonics, may be induced by the impact of meteorites. For instance, there is now, I think it's not well substantiated, hypothesis that building huge dams, like in China they are doing now, the Three Gorges Dam, these are very huge dams, the largest dams in the world, may change the behavior of the Earth's orbit because it's concentrating a lot of weight, water is very heavy, in a specific place. I don't think this is reasonable, but just to give you an example that these changes of climate can be also caused by movement of continents or changes in the displacement of the inner part of the Earth. And I would say that we can stop here. Let me just say, okay, here it's talking about the great acceleration, and we already talked about it. And I think that here we are. Okay, thank you, and I apologize once again because I started a little bit late, and see you next Monday. Don't forget Wednesday, the lecture by Professor Domenighetti. And in particular, the first one, I suggest you to attend, but also the other ones. But the first one is delivering some information that is important. You can attend online anyway. Okay, very good.